Despertamos. En distintos puntos de la región se activan los sentidos. Nacen ideas. Se desarrollan nuevas oportunidades.
Hoy nuestra alma mater saluda a esta comunidad universitaria que todos los días extiende su presencia por la región y el mundo.
Se materializan sueños que transmiten el espíritu emprendedor y la inventiva humana. Cuando se cuestiona la técnica a través de la ciencia, nace la tecnología. Se despierta el ingenio, se crea una nueva historia. Somos la Facultad de Ingeniería de la Universidad de Antioquia. Un lugar para poner en movimiento la sociedad a través del aprendizaje. Una plataforma para la vida, el bienestar, la ciencia, la creación, la tecnología, la innovación. Un sistema de saberes, talentos y prácticas con las que se potencia la naturaleza de manera eficiente, sostenible y accesible para el beneficio de la comunidad. Somos ecosistemas que se conectan sobre la cordillera de los Andes. Atraviesan montañas y páramos, se mezclan con ríos, selvas y llanuras que llegan al mar y se hacen océano, región, territorio. Un universo de posibilidades. Un puerto desde el que se construyen puentes para pensar el campo y la ciudad. Somos pioneros porque más que una fecha de fundación, hacemos parte de la historia. Somos un lugar para motivar debates por la libertad y el conocimiento, abrir y trazar caminos, conquistar nuevos comienzos, descubrir y desarrollar capacidades para el progreso y el futuro. Somos formación porque acá no tenemos que ser genios universales para hacer historia. Somos una comunidad para potenciar el ingenio, encontrar una especialidad y tras un completo entrenamiento en ciencias básicas, exactas, humanidades e ingeniería, ampliar la mente, experimentar, navegar, cambiar de estado, desafiar la gravedad, agudizar los sentidos, aliviar la respiración, dar un paso más, buscar nuevas perspectivas, proponer alternativas. Somos ciencia, tecnología e innovación. Tenemos tantas ideas como estudiantes, profesores, investigadores, egresados y aliados. Nos inspiran las preguntas sobre nuestro entorno. Creamos puntos de encuentro entre saberes. Trazamos líneas que comunican la aplicación con la creatividad. Diseñamos y ejecutamos propuestas, estrategias y metodologías para descubrir, crear y transferir conocimiento. Ponemos en movimiento la imaginación como insumo para la industria, la aplicación social y la protección del medio ambiente. Somos rutas para la transformación, un lugar en el que se encuentra el conocimiento y la sociedad para resolver problemas comunes. Somos laboratorios para la experimentación y el aprendizaje. Fabricamos experiencias, tejemos vínculos, creamos proyectos y servicios. Acompañamos iniciativas para el desarrollo de nuestros territorios y sus pueblos. Somos una red que trasciende los límites físicos para generar nodos de aprendizaje, experimentación, juego y encuentro, mediante proyectos que amplían la cobertura de la educación virtual regional. Somos expansión, evolucionamos, hacemos acciones locales y regionales con impacto mundial. Construimos puntos de vista que cruzan fronteras y amplían el horizonte. Somos ingenieros globales. Nos apasiona explorar la profundidad y la inmensidad de otros mundos. Conquistamos y exploramos universos posibles, sembramos estrellas, intercambiamos ideas, culturas y saberes. Elevamos nuestra voz, hablamos distintas lenguas y lenguajes. Somos gestión, planeación, liderazgo, memoria, patrimonio, comunicación y divulgación del conocimiento. Narramos el saber y documentamos su aplicación y enseñanza. Somos bienestar, trabajo en equipo, disciplina, orgullo y expresión. Desde distintos puntos de la región, irradiamos un conjunto de señales en el tiempo y el espacio. Somos un mensaje que conecta nuestra historia con la de muchas historias más. Somos parte del alma, somos ingeniería, somos Universidad de Antioquia.
Good morning, everyone. For me, it's a great pleasure to introduce you the Professor Devasis Chanda from the University of Central Florida. Professor Chanda works in the Department of Physics Science, specifically in the studies of life for many applications. For us, it's a great honor to have the professor here in the University of Antioquia. Professor gave us the conference sensitive detection of neurotransmitter dopamine using plasmonic biosensors. This is a very important area of development in the world academic field. So for us, it's a great pleasure to have the professor who gave us the conference. Professor, the audience is yours.
Thank you, Anna, for the kind introduction and the invitation to come here to give a talk. So I think, as Anna said, I belong to University of Central Florida and appointed with Nanoscience Technology Center, Department of Physics, and also College of Optics and Photonics. These are three independent departments, but there are a lot of overlap, like a lot of nanoscale device being made at the first institute. Physics is the fundamental department where a lot of physics, physical phenomena or research takes place, and optics is one of the area UCF or University of Central Florida is quite strong and big. So so that's kind of brings me a very multidisciplinary researcher where we are working on a system where we are developed a biosensor based on plasmonic sensing platform to detect neurotransmitter dopamine, and I'll try to talk in my presentation why it is so important and where we need for the society to understand brain much better, simpler and more accessible way. So this is one of those area I think have a lot of promise for us to develop further. So with that, so let me just outline. So I'll try to talk about the importance of neurotransmitters, because that's the brain, how brain function with neurotransmitter. Then I'll introduce a sensor we are working for quite a few years. We call quasi bound in continuum, the quasi BIC biosensor. And then within that we have to try to highlight how this biosensor is functionalized to detect specifically a neurotransmitter called dopamine. And there are two different schemes we used before, and both the scheme has own merits and demerits. One using an inorganic agent functionalize the surface of the sensor, and the next one is more advanced, more of we call aptamer based sensing platform, where we functionalize the sensor with aptamer, which selectively bind dopamine from the bloodstream. And again, I'll try to conclude with some prospect, like where we plan to go, where this can lead us to. So again, we all pretty much have knowledge about that neurotransmitter, actually chemical messengers that transmit signal across synapses between the neurons. Means this neurotransmitter actually work as a communication channel between the synapses in the brain, and it is extremely essential for proper functioning of the neural system, our cognition, emotion control, motor control, means how we walk, how we do daily stuff. So those are the things extremely important. So there are kind of four major neurotransmitter we can look into. One is a dopamine. Again, let's go slowly because these are important to understand. The dopamine is actually helps human to improve socialization skills, physical touches, all these, touch and animals and all these things, emotions like helping others. So those, all of them actually controlled by dopamine. Means if somebody feeling depressed, isolated, he or she probably has a dopamine deficiency. There's also other neurotransmitter called endorphins. They are basically controls kind of more of a painkiller. Exercising, listening to music, watch movie, laughter, all of those they control. Oxytocin is more of a love hormone, means eating food, what food we love, achieving some kind of goal, complete a task, self-care activities like how we conscious about ourselves is controlled by oxytocin. And then serotonin is actually more of a mood stabilizer, means like in the sun, how we feel on the beach, say for instance, how we feel in the outside, how we remind ourselves many things, how do you do meditation, all of those actually controlled by serotonin. So these are the few neurotransmitter, major neurotransmitter which actually controls some of the key attributes of our brain activities. And in this case today I'll be talking about how to detect dopamine, which is actually one of the main neurotransmitter which controls a lot of our major activities, means how we walk, how we touch, how we feel, how we interact with other people. So those all is controlled by dopamine, which basically significantly important for us. So now what happens if what is the main goal, why it matters? Like imbalances in neurotransmitter, if neurotransmitter concentration go low or high, it creates a lot of disorders. Like we know about Parkinson's disease, Alzheimer, schizophrenia, and ADHD. Of course, there are many such neurological disorder takes place. A lot of clinical relevance is that if we can detect those neurotransmitter. So our goal is to really have this simple blood test based detection. If you can detect those neurotransmitter from simple blood test, it actually improves our well-being. We can monitor our health and the brain activities. So that's what the kind of main goal of that. So just to dig a little bit deeper into the one we'll be talking today is dopamine. So it's basically called feel-good hormone. So it's electrochemical neurotransmitter. It controls our cognition, behavior, motor control, and irregularities in dopamine level in blood or CSF have been. So basically, if the dopamine concentration changes in cerebrospinal fluid in the brain itself, and and or in the blood. So that can lead us to, just a simple example how this neurotransmitter move. This is a cartoon way of simple showing that it can spread like that. Gives us pleasure and happiness. Need more bigger spread of dopamine across the brain. So it's kind of pictorial, can show that from pleasure to happiness, the dopamine need to spread differently or transmit differently across the synapses. So, and again, now if dopamine concentration is irregular, means if concentration lower, then it can lead us to neurodegenerative disorders like we all know, and society is suffering for Parkinson, Alzheimer, and then there are a lot of neurodevelopmental issues takes place mostly for the kids, like ADHD is one of them. Psychological condition like a bipolar disorder happened. A lot of neurological brain cancers takes place. So basically monitoring dopamine level is extremely important just to for all kinds of neurological disorders. Here more of a kind of pictorially showing a healthy patient how neurotransmitter dopamine goes from a receptor cell, from a transmitting cell neuron to a receptor cell. It actually transmits with the given concentration or given number of dopamine molecule transmit from neuron to the next neuron. But here, when somebody has a Parkinson patient actually has some blocker, means not enough dopamine to transmit from the transmitting neuron to the recepting neuron, just because of the concentration is pretty low. So that basically shows us that to monitoring dopamine concentration is significantly important for us. So what is the main challenge? So the main challenge of detection of dopamine is that there are quite a few similar molecule which is called catecholamine molecules of dopamine. They are very similar to dopamine. Just pictorially you can see that dopamine has a chemical formulation like that, but now if you compare with L-dopa, adrenaline, noradrenaline, dopac, all actually has very similar kind of benzene ring and then some extension of that benzene ring. So basically they are chemically quite similar. That means it's very difficult to identify whether you're detecting dopamine or say L-dopa or say dopac. It's quite difficult to do so. So that basically points us to the point that direct detection from a complex matrix is difficult. Means from detection of dopamine from directly blood is quite challenging because it has a multiple similar neurotransmitter in the brain and difficult to detect them. So how people does at the present state of the art? So traditional dopamine detection methods at the present is HPLC, which is basically high performance liquid chromatography. There's ELISA test, enzyme linked immunosorbate assay, and there are electrochemical methods. And then what are the limitations? First of all, limitation is it requires complex samples preparation. Means to detect dopamine it needs many steps to really do so, and many times you need cerebrospinal fluid, means you make a hole in the head and draw the CSF from the brain. This makes things extremely complicated, and then they are extremely slow process because it has to go through so many steps, and also sensitivity and selectivity quite low in dopamine detection. So what is the solution? So this is the state of the art. We are talking about that there are few techniques like HPLC, ELISA out there, but they are not very day-to-day testing methodology to monitor dopamine. Like somebody going through a phase of mood swing or depression or unhappiness, you cannot every day do a ELISA test on some person, which is not practical because it's such a long, expensive process to do so. So that means it brings to a point that we need a point of care, means a simple technique where you can actually detect dopamine, like we do glucose measurement in the morning. You drop a blood, and then you know your glucose in the in the bloodstream. So that is the whole goal here, to really do a blood test development for to develop a blood test. You just drop a blood, and then like a normal blood sugar test, and you can measure the dopamine concentration. So that kind of the whole goal of the process. And now I try to highlight why dopamine, why it is important, because it is helps us cognitively, it controls our mood, and it controls our well-being. So it is important neurotransmitter, and also it controls significant diseases like Parkinson and Alzheimer, where a big portion of the society across the globe suffering because of these diseases. So the question is how to detect them directly from blood. And I was also mentioning that it is not easy to detect from the blood, because dopamine has many similar other neurotransmitter in the brain, and also on the bloodstream. So it's not straightforward to detect dopamine just like that. So now I will switch gear to talk about a sensing platform. So this sensor, again, this is more about optics and optical physics oriented, that it actually has a plasmonic pattern. So it's basically gold pattern, about 1 micron period, and say 500 nanometer hole diameter, and it has two components. So this sensor, if I break it down, so it has kind of hole disc structure, means it has a gold pattern on the top, hole pattern, and the disc on the bottom, so the hole and disc. And then we attach this whole disc to a optical cavity. So from optical engineering standpoint, when you attach a plasmonic system where you excite surface plasmon with an optical cavity, you can actually coherently increase that resonance condition. So this sensor actually has a two component. One is this perforated gold pattern, and then there's a disc, and it is also attached with a cavity. So if you add them together, it looks like that. So it basically has a dielectric spacing layer, it has a back mirror which is bounces light back, and there is a perforated gold on the top, and there is a disc in between. So disc in between, hole on the top, gold hole on the top, and there's a dielectric spacing layer which basically supports the light who comes in and form an optical cavity, and there is a mirror and it bounces back again. So that's what the work, and I'll try to highlight how it does work. So when at resonance, we can actually see that if we just look at this system here, this cavity system, like a Fabry-Perot cavity, is a thin gold and a thick gold, and this dielectric layer, when light comes in, it creates a Fabry-Perot cavity, and you change the length of the cavity, so you change the cavity thickness, you change the cavity resonance. That's what you can actually see. But now you add this plasmonic system with this cavity to make it this hybrid system. Now you actually see that this overlap of these Fabry-Perot modes with the plasmonic mode here create very complex distribution of the mode. Means you create a lot of these resonances, means light will get sharply absorbed at certain wavelength, which I will highlight in a minute. So you actually create a lot of those resonances. Means you can choose a cavity thickness, say 600 nanometer, and you can actually use a resonance, say around 750 nanometer. That's a resonance you can use to detect, which I will try to highlight in a minute. So basically, if I now look at that, what is the advantage of that? This is a geometric sensor, is geometrically tunable by changing the period or the diameter of the pattern on the top, or the relief depth between the hole and the disc. I can actually change the resonance location, and then we can actually see that when a system like that, it has a very sharp resonance. So basically, if you send a white light from the top at around 850 nanometer, you get the light get completely absorbed. So let's not worry about anything else, just look at this mode. When the white light comes from outside, you shine it, so everything will be kind of reflecting back, but around this 8.5 nanometer, that light gets strongly absorbed in this system. And if you look at the system, the top view look like the optical mode, it's a kind of dipolar resonance on the top, and then you can also see the coupling between the top hole pattern and the bottom disc pattern, and then this coupling actually helped by the resonance, I mean the Fabry-Perot feedback mechanism. Light comes in and there is a back mirror, it reflects back. So if you choose the cavity thickness appropriately, you can actually coherently enhance this interaction. Basically, you can make it completely non-reflective for one particular wavelength, means completely that portion of the light get absorbed. So our goal will be to use that resonance to sense a molecule. That's the ultimate goal. So even it is in a given short talk, it's impossible to convince the whole optical physics behind it, but the take-home message that a sensor like that, when you illuminate with light at a given wavelength, say in this case 850 nanometer, no light reflects back, the light gets completely absorbed. So that's my resonance peak, and our goal is to use that peak for a meaningful purpose and see if we can sense something. And for this one in particular, the period from here to the here is around 580 nanometer. The diameter of the hole is 300 nanometer, and the relief depth, the gap separation between the top pattern and the bottom pattern is 380 nanometer. So now, what is the ultimately, optical physics is separate different talks I try to highlight, but the bottom line is that our goal is to functionalize this sensor with some kind of reagent so that it selectively detects or attaches dopamine from the blood. So here we can actually see that the blue line is the actual resonance of the sensor, means at around 850 nanometer no light reflects back. You see that reflection goes to a null and comes back up. But if you attach a molecule, you modify this surface, you see the resonance location shift. So that shift we measure. So the whole goal is that we want to measure the shift of the resonance, because say now if you add the surface modify with another molecule, it actually the resonance location from blue it goes to red, and this shift is about few nanometers. So our goal is to measure the sensor as a function of this concentration. So if you change the concentration of the molecule, the light which is resonating at 850 nanometer, it will start resonating at 852 nanometer or on that same length scale. So basically you shift the sensor resonance as a function of the molecule which you are adding to the surface of the sensor. So our first goal was to do the surface modification using an inorganic agent, and we started with something called Ceria nanoparticle. So this is a bare sensor look like, and then we added a Ceria nanoparticle, and then Ceria nanoparticle strongly attached dopamine. So what it does, that now if you do not add this surface functionalization layer, in this case Ceria nanoparticle, it cannot distinguish whether you are attaching dopamine or any other molecule. But here the Ceria nanoparticle has a selective detection to dopamine, so it only attaches dopamine from say blood. So when you flush a blood on the sensor, again I'll show more, it actually selectively binds dopamine and let all other molecules pass through. So basically it makes a selective detection technique. So here it can be shown that we are actually measuring from a simulated body fluid is SBF. It's basically not blood but blood-like. So before we jump into the blood, we started with CSF. So we can actually see that we're changing the concentration of the dopamine, say tens of femtomolar to 1 micromolar, and you see that more and more dopamine you add, your spectral shift increases, and that's a spectral shift. Remember, the first red line is the original sensor without any functionalization. The black line is the when you functionalize with Ceria nanoparticle to make it selectively attack dopamine, and the blue line is when you add a dopamine or flush of blood, it attaches blood dopamine. So and then you subtract from the blue line to the red line, means the resonance location of red line minus resonance location of the blue line, thus give you the spectral shift. And that spectral shift here called localized surface plasmon resonance shift is correlated with the concentration. So more dopamine you have, your spectrum shifts. So basically for our measurement, we have this calibration curve. We send the blood we measure a spectral shift of, say for instance, 3.5 nanometer, spectral shift at 3.5 nanometer. If I know 3.5 nanometer, I know that dopamine concentration is 1 nanomolar. Same as if I measure, you flush a blood and we found the spectral shift is 2.5 nanometer, and I know 2.5 nanometer correspond to 1 picomolar concentration of dopamine. So basically, having this calibration card, now I can randomly measure dopamine concentration from blood without knowing anything, because now I know that my sensor is only attaching dopamine, no other molecule. Just to show that, we also do some fouling study that we added dopac, ascorbic acid, epinephrine, and then also the dopamine, and you can actually see that because of the serial nanoparticle is selectively binds dopamine and not other neurotransmitter, so they are kind of below the baseline, means we can actually ignore them, and then for same given concentration we see the much stronger shift with dopamine compared to, say, epinephrine, ascorbic acid, or dopac. So basically it is saying that even though there are other neurotransmitters are present in the blood, but we can still pick out dopamine directly from the bloodstream. So that's what I was showing how the chip look like. This actual picture in the lab where blood comes through and passes through. So this is a more better picture. So we had the first generation of this work where we use this serial nanoparticle to attach dopamine. So we send a bloodstream and blood goes to this plasma separator, because we have a lot of red blood cell in the blood. So we separate the red blood cell, it goes back to dump, and the plasma goes inside these small channels, and light comes from the top and make this reading of the dopamine concentration as a function of spectral shift. That's how I was kind of mentioning. So you can actually see that blood comes in, and this is a process called hydrodynamics. When you push the blood through, all the red blood cells goes this way, and the plasma, the clear liquid, goes the other way, and you measure the dopamine concentration from the clear liquid. So this is what we are actually measuring, that quite a linear relation between concentration of dopamine versus spectral shift in plasma. So we are actually separating, taking a blood, and the chip itself separate the plasma, and from the plasma we are detecting dopamine. So now the still question is how it compared with the present state of the art. So these are the established technique, like HPLC is very popular. HPLC has electrochemical technique, colorimetry, fluorometry, mass spectroscopy, ELISA. So typically they are into the depend 1 to 6 nanomolar detection limit, means it can detect up to that, and we detect up to 1 nanomolar. Quite comparable, and many times could be better than some of the technique. But then many of those techniques are not really accessible, takes very long time. For us is a few minutes time, and then we do not need sample preparation. They need a lot of lab sample preparation. Like the first one is CSF, means cerebrospinal fluid. Cerebrospinal fluid means you have to drill a hole back of your head and draw CSF, which is itself a scary, intruding, expensive, difficult process to get CSF. It's not really easy. From urine probably better, but then it needs lots of pre-processing of the sample. Here we do not need any pre-processing, we are directly detecting from the blood. So it makes lives much easier, simpler, more accessible to the point of care application. So the next generation of the work, that's the first generation of work we did where you use serial nanoparticle to functionalize. But then also we found the serial nanoparticle has some kind of self-life, and it deteriorates, and we are struggling with reproducibility sometime, because serial nanoparticle size, every time you synthesize, the size changes and its binding to the dopamine changes. And so we moved to a new technique based on aptamers. So aptamer actually a single stranded oligonucleotide could be RNA, could be DNA. So basically you can think of that it is actually a process called Select process, where again more of a biology part, which is not part of my talk, but Select process means you know the target. In our case, the target is a dopamine, and you actually have a library of RNA in this case, or could be a library of DNA, and you selectively see which one binds to this target. So you do this process again and again and again, and through the Select process you find out a RNA or DNA chain which actually selectively binds to dopamine. In our case, it could be anything, could be virus. Dopamine more selectively than anything else. So this is a process called Select process. Again, it needs a full talk, its own merit. So I'm not going to dive into too much into Select process, how to design aptamers. But it's basically single-stranded oligonucleotide. So basically, it could be RNA, single-stranded RNA or DNA, and it is basically has affinity towards a given molecule. And in this case, our case, a dopamine. So what is the advantages? The excellent specificity means we found that it actually binds with dopamine, in this case extremely selectively. So long shelf life means it does not deteriorate over time, and quite stable. So that's what I think we had a problem with serial nanoparticle, that stability was that deteriorating the performance. So this is, we found extremely stable performance. So then we studied two different kind of aptamer. One is 57 mar, and then one is 44 mar. One is longer, one is kind of shorter, and both of them actually binds to the dopamine. So what to do? The whole process, you have the sensor, you functionalize with this aptamer, in this case a single-stranded DNA aptamer, and then now the question is, aptamer will only bind to some areas, but there will be some open gold area, you want to block them up. So basically you use MCH 6 marcaptohexanol, which actually cover the remaining area, whichever area not covered by the aptamer, so that you do not want any fouling. You do not want dopamine to sitting on the gold. You want dopamine only to be attached to the aptamers. So it basically prevents biofouling. So that is basically what we are looking at. When you send the blood has so many other neurotransmitter, other protein, other thing, but your aptamer is only designed to bind with the dopamine. It does not bind to anything else. So you flush it up, the whole blood matrix, it has thousands of various molecules, but none of them binds to the surface, because this kind of lock and key arrangement. Every lock has its own key. So same thing, this aptamer has a very specific structure. It only binds to, in this case, dopamine, right? So you can actually selectively bind dopamine from the blood and flush it up, and then you bring the light from the top, and light bounces back. So we do measurement before blood here with the sensor, bare sensor, and with the dopamine present, and we subtract the spectrum, and the spectral shift I was mentioning, that correspond to your concentration. Higher the shift, higher the concentration. That's the bottom line. So this is basically kind of shows before functionalization, means before this step, and this is after functionalization. We can actually see these aptamers kind of sitting. Again, this AFM scan not really show, but just we wanted to make sure that after functionalization, aptamers are there. So now these functionalized surfaces kind of look like that. It just appeared few weeks ago in Science Advances journal, this present work, that so our goal that determine appropriate aptamer for dopamine detection, which I was mentioning. First, to design the aptamer, do some control tests so that interfering species like other neurotransmitters should not trigger your sensor, it should not be detected, and also find out limit of detection. And we did from bovine blood, and also like a bovine serum, and we did from artificial CSF, artificial cerebrospinal fluid, basically artificial brain fluid, and then whole blood. So this sensor kind of look like that. I was introducing the top view. This is the actual sensor electron microscope picture, and this is the cross-sectional view. You can actually see the top, the hole pattern. These are the hole, and there's a middle disc, and there is a cavity. There's an optical cavity. There's a back mirror. So that kind of shows how this sensor look like, and this is kind of pictorially, schematically show how the sensor look like in real chip. So this is a chip, the microfluidic chip. Blood comes in, goes through these channels, and kind of comes out. And when it comes out, the sensor, this somewhere sitting here, it is actually selectively binding a dopamine. So we actually created this serpentine pattern to control the flow of the blood. It gives us time to make the blood flow through the sensor. This is basically more of a fluid control. And then when you control the fluid, then you, because if you pump the fluid or blood here, it will go directly. So you want to slow it down through this serpentine design. And when it passes through this sensor, it selectively binds this dopamine. So here it kind of shows the sensor selectively attaches dopamine and remaining blood flashes through. After we send the blood, we flush the whole thing with a buffer solution, clean the sensor, light comes in and then bounces back or reflects back, and the spectrum shifts, and then from spectrum shifts we find out the dopamine concentration. So we did study on two aptamers. One is this 57 mar and one is 44 mar. And what we found, this 57 mar being a longer chain is basically protrudes out, and we found that it attaching to dopamine is not very accurate. Means it does not really have a linear relation of spectral shift when we add a dopamine. But here with this 44 mar, when we add a dopamine, we see a much linear shifts of the spectrum. So this is, we chose, main reason is a much shorter chain. So this single strand DNA is much shorter chain. So basically it is much shallow, means it is not away from the sensor, and we found that has more selectivity than this longer chain aptamer. So we chose that one, and we went ahead. First we started with phosphate buffer saline. We add dopamine inside PBS solution, and this is a very standard technique. You create a buffer solution and then you measured dopamine concentration. This is a dopamine concentration as a function of spectrum shifts, which I was mentioning, and you can actually see there's a baseline, means we could go up to like a 1 nanomolar or just a low. So this is the kind of detection limit, because beyond that is kind of a baseline, means no spectral shift as such as a function of concentration. We want some kind of change. So so that's basically typically a normal healthy people has about 200 picomolar concentration. So about this range. So this is the range we have to focus on. And again we did some control study, means we have a dopamine and in the blood, and also we had L-dopa, epinephrine, dopac, HVA, homovinylic acid, which is HVA. And you can see none of them actually detected. Means in the blood you have all of them, and none of them their spectral shift is extremely small, so you can neglect them. But with dopamine, because the aptamer only binds to the dopamine in the blood, remaining all other neurotransmitter just passes through, is not bind to the surface, so it does not make any spectral shift. We found excellent selectivity with dopamine detection. So now we started with BSA, which is bovine serum albumin, basically a serum extracted from cow blood, and that's the detection we did to start with in a dopamine in BSA solution. We see a nice trend there. As expected, below 1 nanomolar we could detect pretty well, to 1 nanomolar to hundreds of picomolar range. And then we did the same measurement also on artificial CSF, which is cerebrospinal fluid directly came from the brain. So we just wanted to show that we can also detect from any solution, from brain fluid to blood. Ultimate goal for human trial, we want to do collect brain CSF, also blood, and establish a correlation between dopamine fluctuation in the blood and in the brain. So that's the reason we cannot pursue the CSF measurement. So it look like nice. We can have similar measurement in the CSF. Again, that's a chip look like. One interesting point I can point out that in this chip that we do not, this next generation, we did not have a plasma separator. We got it out. Means we are directly sending the blood, and then the blood goes through directly. No plasma separator. In the first generation were with a serial nanoparticle, what we did, we actually took the blood, and the chip itself has a plasma separator. So only from plasma, which is a clear liquid, we detected here. Because of this higher sensitivity of the aptamer, we could actually bypass the whole process of plasma separator on chip. So it directly detecting dopamine from the whole blood, no plasma separator, which is excellent progress in that sense. So blood, you send the blood goes through the serpentine channel to slow it down, and then it goes through sensor, where sensor is sitting here, and it selectively attaches dopamine, and light comes from the top and measure. What is the important point? Another important point it adds that you can actually do this measurement real time. You can actually draw a blood, normally in hospital or clinic, you can hook up a blood drip, you can actually draw this blood and continuously monitor. So basically here we are actually sending the blood and through the chip, and then we are changing the concentration of dopamine. In this case it's not a human trial, so we are artificially changing the concentration from 1 micromolar to 10 nanomolar, and this is a control, means it has no dopamine in it. So basically if you subtract this shift, then this shift, and plot the spectral shift as a function of concentration, we found a very linear relation between spectral shift and the dopamine concentration. So what is the advantage? Advantage here is that you can measure dopamine concentration real time. How mood changes, how somebody's mental health changes, you can actually monitor throughout the day. You can collect data whole week, you can take every day and measure. Other technique does not allow us to do so, because you have to take the blood to the lab, you have to process and do all other things to get the measurement. Here is a direct measurement. So basically you send the blood, this is where the blood starts flowing, and you detect it and stop the blood, you do not need, and then flush it with the buffer solution to clean the chip, and then start the blood again, flow the blood, and then every time the blood flows through, if there is a change of concentration of the dopamine, the spectrum shifts. You can look like that. From 1 micromolar, you have more shift. The gap between this line and the baseline, this gap is much higher compared to 10 nanomolar gap. So basically the spectrum shifts as a function of concentration, and you can do it periodically, right? So basically this can be done on and off throughout the time, and you can actually monitor somebody's dopamine fluctuation as a function of days, weeks. So no assay preparation needed. That is the advantage. It allows us that you do not have to take the sample to the lab to do all the assay preparation. So this work got quite interesting worldwide news all over the world because of the its simplicity, its appeal, its applicability, its point of careness, that it can be used all over the place relatively easily. So that's something extremely important for this stress to really focus on Parkinson's disease, Alzheimer, depression. There are many such neurological disorders can be kind of measured. So the future prospect actually, what are we looking on, that this kind of next step for us is the human trial, where we are working with few Florida hospitals, and also are looking for opportunity to other places, hospital including Colombia, because we need sample, means people having some neurological disorder, their blood sample we need to really establish human specific measurement. This is still not a real patient's blood. This is all done through a cow blood. Actually, cow blood, bovine blood, we spike with dopamine and did all this sensor development. But ultimately, all this measurement we want to do on human blood with human subjects. So we're going through all these regulatory requirement and looking for more collaborations. But there are many things. Our plan is to do multiplexed detection, means not just dopamine. You can also measure same chip, say serotonin, oxytocin. So you can actually measure or epinephrine or L-dopa. So you can actually measure the same chip, all of them, because every chip will be functionalized with its own aptamer which only attaches to one given molecule. So if you want to detect serotonin, you design the aptamer which only attaches to serotonin. So in a single measurement, you can actually have whole panel of neurotransmitter detection done. So that's something what will be pursuing, making it more miniaturized so that it can be transportable to a smaller clinic measurements. That's what we'll be doing. I know again in a future, of course, it can be made into wearable sensing platform where you can actually have a prick of a blood can show your dopamine concentration. And it's a non-invasive test, means you just do not need to drill holes and in the brain or all kinds of other complicated thing. And it can help us do a lot of early detection, means you do not have to wait too late for that kind of measurement. So with that, the work was funded through National Science Foundation in United States. So it's kind of quite interesting. This work will be now part of a National Science Foundation report to the President of the United States. In October, I have to give interview for that. So it's kind of exciting to see where it goes, how we can take it to the next level for human trial and eventually commercialization. So that's what I think we are behind now. Got some venture capitalist investment already. So we're kind of quite excited to see how we can make it more packaged, more accessible, and more take it to closer to the clinical trial. So with that, I will stop. Thanks for your attention. I'll be happy if there are any questions. So these guys are gone.
Professor, how do you create the plasma?
So
how do you feed the chip to create the plasma? How do you do that?
So the first generation of work, we actually needed a plasma separator, but not second generation of work we got rid of it. We did not aptamer based system. We did not need a plasma separator. So here in this technique, the first technique where we created this hydrodynamics flow method, is a very well known flow methods. Like a river, when river goes through a big bend, in this bend all the mud accumulates and the clear water goes through other channels. So this is a very known hydrological problem. So the hydrology people do all the time to make the canals. They actually create this kind of bend so that the bend, all the dirt goes one way, clear water goes other way. Because of the hydrodynamics, when you make a big bend, all this heavy particle cannot go make this bend. As soon as you make a circle, it makes a tangential motion. It follows this way instead of going that way, because you create a rotation, right? And so particle try to say in this case red blood cell, we want to get rid of red blood cell and have a clear plasma. So clear plasma we could create. But this is the first generation of work where we had trouble with measuring direct from the blood, because red blood cells are big and they are kind of fouling with our measurement. But the next generation of work, which I was just talking about with aptamer, before our first one was with the seeded nanoparticle. So this aptamer based technique where we do not have plasma separator, direct blood. This is just direct blood. That's it. Because this is very sensitive. These these aptamers. It does not matter. It does not even bind to a red blood cell. It just attaches the target molecule, and everything you flush it out. So that makes it more practical. More simplistic you make, it makes practical. More cheap as complicated setup, you have more chances of failure. Because for plasma separator, we needed to maintain a proper velocity. With the pressure and velocity we maintain so that when it bends, red blood cell goes other way and plasma go other way. But the pressure is higher, then some of the red blood cell will go both paths, this path and that path. That's hydrological design. The people who design canals and the river, they have to do all of those. And you see during rainy season, their design fail again because water pressure is different. They want to have some canal with a clear water, but it failed in a season because pressure is different. So having a plasma separator, you need to have a pressure controlling mechanism. Here, nothing needed. So which is make it more simpler.
And do you have this exact measure? Do you have a exact measure to detect in the device? For example, how do you know the quantity of dopamine? If you change the quantity, for example.
So here are changing the concentration of dopamine. So 1 nanomolar to 1 micromolar, and the corresponding spectra shifts. So basically we are measuring the shifts of the spectrum, and that basically correlate to the linearly depend on the if the spectrum shifts is 0.6 nanometer, then the dopamine concentration is 100 nanometer. So we measure the spectral shift, and we have this graph relation between shift and the concentration already calibration done. So you just measure the spectral shift and find out the concentration.
Professor, we have a question here from Manuel Alejandro. He says, how long could it take to use the sensor on a clinical trial, and if it is possible on the market?
Right, the whole measurement takes less than 15 minutes. It is a real time. Even this is a real time measurement, no delay in it as such. But yes, so that's what we are behind, and of course we'll be looking into collaboration that we want to take it to human trial, because at the moment everything is based on bovine blood, means cow blood. So our goal is to now go to human blood. Human blood has a lot of regulatory requirement, because in United States you cannot just work on human blood. It has to be approved by all the authority, including FDA, so that you can run a trial on human patients. So yeah, that's our next step. We are hoping that sooner we will have progress onto these human trials. But overall, this measurement can be done instantaneously. It's like a real time. You see, this is a real time measurement. You send the blood, it keeps telling you the dopamine concentration at a real time.
Same person have another question. What could be the process to adapt the sensor to detect other proteins like phosphorylated in patients with Alzheimer's disease?
So question is, yes, it's simply here this sensor itself has no affinity. Means sensor itself does not know what is dopamine or what other molecule. The whole detection process selectivity come from this aptamer. So if for a molecule X you design the corresponding aptamer which binds to the molecule X, and that's it. Then you detect molecule X instead of dopamine. So the sensor itself does not determine what molecule. They determined by this surface functionalization layer, in this case is aptamer, which selectively bind. Basically a lock and key measurement. So you have a lock and you need to have a key. So this is the kind of setup. You have a molecule X, and then you need to have this aptamer which binds to molecule X, and that's it. Then you take molecule X instead of dopamine.
Right.
A little more details of the detection is what is the machine or the device?
It simply need a spectrometer, small spectrometer. Small, not a FTIR or anything like that.
No.
Any small spectrometer, like a few nowadays spectrometer, few $1,000. That's it. And these are very common nowadays. Every clinic, they call platelet reader, but every clinic around the world actually they have a spectrometer in it. It's a visible spectrometer, not infrared. It's very cheap visible spectrometer covering the visible spectral range. So this is all visible domain. We're looking into all visible domains. It's not a infrared domain. I'm looking at the spectrum. Here probably. Here, it's all visible spectrum domain, around 800 nanometer. Very cheap spectrometer.
And how do you do the gold?
So we actually deposit gold with electron beam. That's a sensor fabrication steps. So that's what we fabricate the sensor. We have a very simple technique.
Is lithography?
Yeah, we use nano imprint lithography. We just emboss a pattern so that make it more cheaper. You do not have to go to clean room. We can make it in your lab if you want to. I'll send you bunch of sample. This making in your lab is just nothing. because you purposefully we did not use the UV lithography or E-beam lithography. This is simply nano imprint. There's a stamp like a mold, and take a polymer, like this is a polymer, you just imprint it and you create this pattern and then deposit gold, that's it. Like E-beam evaporator or any evaporator, put a gold of 30 nanometer and then you are okay, sensor is ready. All the design take place already, so you don't, all the design is in the mold. The sensor actually in the mold, you just emboss it, deposit gold, you are ready.
Yes, the target to the cost of this kind of sensor is more or less what? The
Cost?
target of the cost.
Cost is like, I don't know, extremely small, because it has very tens of a nanometer thick gold and some dielectric polymer. There is nothing much to that. It is extremely small cost involved.
Cheap,
extremely cheap. So because we do not need more area, it's like a few millimeter square area. And if you talk a few millimeter square area and 30 nanometer gold is extremely small. Say 1 gram will gold give you 1 million sensor at least, 1 gram. That's what I'm looking at. So it's basically extremely simpler. So we are kind of pushing that optimistically. Got some venture capitalist money onto development that. So we're kind of set up this. USA not easy human trial. It's extreme world's most complicated thing in USA because of regulatory privacy act. Nobody wants to tell they have a mental problem because people blood there, but they right you cannot disclose a mental problem. That's it. You cannot take that blood for any study. We need people having some issue. Yes, normal. We have to control normal people with issue. Then only we can get the information, right? So it's not easy. So we are working hard to get that with few hospitals now. So in coming few months, I think we'll have better picture when, where, and how soon we can get this human trial going on.
Okay. Professor, thank you very much.
Thank you for the attention. Thank you for the invitation. Anna, as always, pleasure to visit.
Thank you for the collaboration.
Yeah, I think this is something we should try to set it up here. The small spectrometer, $2,000, and easy setup so that you can start making some sensor chip. Not just for this other thing, detection of like a pesticide, some agricultural product. From water, some contamination you can detect. So many other things can be done.
Yes. No. A lot of applications.
Right. So you can do many other things. This is just one example of that.
Thank you so much.
Muchas gracias, Jorge.